And now let me present another team, another participant, ESoWC. The developer named Ashwin Samudre, and his project is based on deep learning techniques to detect and track tropical cyclones.
Hello everyone. So yes, so as part of ESOC 2020, I worked on a project called Exploring Deep Learning Techniques to Detect and Track Tropical Cyclones. I worked on this project with my mentors, Linus Magnusson and Pedro Maciel. It was overall a really good experience to work on these, finding new techniques to mainly work on how we can actually detect the tropical cyclones, which are very causing much damage these days. So yes, so mainly the introduction. So tropical cyclones are mainly the complex events that are observed on Earth, and accurate prediction of these events is essential and to make the reliable warnings. Cyclones are mainly located and aggregated into subtypes based on their intensity. And previously, these were classified based on using manual techniques like Dvorak techniques and their variations. There have been previous attempts to tackle these problems using AI methods, which is mainly along the lines of image classification as well as intensity tracking. And in this project, we focus on object detection and subsequently tracking the cyclones. So the data that we have, it's mainly divided into different types of cyclones. Initially, it was mainly into this variety of types called 18B, 08S. These are based on this area of the cyclone where it is observed. And so we had a large amount of unnamed ones as well, like unnamed SPC1, unnamed ENP2, and so on. So what we decided to do is to create these, change these classes into 4 major classes. These are based on the pressure values. So the class 0 is based on the pressure values above 1005, and accordingly like class 1, class 2, and class 3. So we can observe that majority of the cyclones are in class 0, and then as we go towards class 3, the frequency of cyclones goes down. So the majority of the cyclones that we have are from class 0, but class 0 cyclones are not considered to be like a full-fledged cyclone. So they are mainly preliminary cyclones. So what we are more interested in is class 1, 2, and 3. But still we have the majority of the data for class 0. Okay, so the data that we have, it's from ECMWF atmospheric analysis database, and it's obtained from the tropical cyclone detection at 6-hour sampling frequency. So we have 4 frames for a single day, and the data from 4 years. So, and yes, so the data is available at different resolutions. So we mainly use 2 types of resolutions, which is 0.1 degree at 8 bit per pixel, which gives us a resolution of 3600 cross 1200, and another resolution which is 0.25 degree at 16 bit per pixel, which gives us the 1440 cross 480 size. So here is an example image of what we have as cyclones. So mainly the annotations that we have are from the ECMWF tropical cyclone tracker, which is applied to the simulated data. And the bounding boxes that we select are mainly based on the observed. We first observe what kind of bounding boxes can be used, and a size of 8 cross 8 degree for this higher resolution worked best for our use case. We actually tried with different degree values, like ranging from 5 to 10, like that goes up to 50 cross 50 of size in resolution to 100 cross 100 plus, but checking the overall features in a bounding box, we settled down to 80 cross 80, which worked good for our use case. Yes, like I mentioned previously, this task has been handled, and there have been previous attempts to use AI methods to solve this. So there has been an attempt to use both like the latitude and longitude values in both wind and pressure, and take the task and for tracking the intensity directly. So in this approach, the authors assume that the detection works perfectly. And in the second approach, what the authors perform is that they take the cutouts and just perform the classification. So they take this task as an image classification task. So we tried this method for our use case as well, and we tried 10 cross 10 degree cutouts, but the results were not that good. And so what we are trying to do here is something in between these 2 tasks. Like both the tasks. So the first task assumes that there's already been detection is perfect and they directly go for intensity tracking. And the second task is a bit preliminary method. So like how we can improve the classification itself. So our task is mainly the middle ground between these two previous approaches. So yes, so as I mentioned, we have formulated the task to be an object detection task. The training data that we have is from 2016 to 2018. And as I mentioned before, we have the majority of the instances for class 0, as well as like for class 1, which is like a good thing to like. We mainly wanted to see how it performs for class 1, 2, and 3. We also have validation data from the year 2019 and 41,439 images. Here we mainly leverage faster RCNN framework with ResNet 50 and ResNet 10 backbone, as well as RetinaNet model based different variations. So this is mainly the architecture details of faster RCNN that we have used. So it's mainly the input image is passed to a convolutional neural network, which is this different backbone networks that I mentioned, like ResNet 50, ResNet 101 that we have used. From the CNN, we get a feature map, which is then passed, and the algorithm like sets out different proposals, like different areas in the image where the cyclone can be, and then it performs this ROI pooling, and finally we get this combined output as the classification output. So it performs this classification and detection in a single method. So this is the faster RCNN architecture. We also tried the RetinaNet architecture, which has this FPN module. So it's based on this where you can do the classification and detection at the same time, and with the help of these subnets. So these are like sub-modules of the overall network, and we can get the final. We have something like a focal loss, which gives us the output of the detection. So these are the recent results that we have for our case. So similar results, same results. I have put it as a graph. So here we can see that the results are obtained at, like as I mentioned, we have different resolutions of data. So we can highly observe that when we have this better resolution, like 0.1 degree at 8 bit per pixel, we get like really good results compared to this 0.25 degree at 16 bit, even at 6 bit per pixel. We actually didn't have the resources to try 0.1 degree at 16 bit per pixel, but that's the next step in our project. Like when we have enough resources to train this on the ECMWF infrastructure, then we are moving there. But even with 0.1 degree at 8 bit per pixel, we have really good results. And these are mainly the mean average precision scores that we got from the different experiments. So yes, so since we only had like 4 years of data, like in total, so we had to do like increase the amount of data that we wanted to perform the experiments on. So the normal augmentation techniques like random rotation, translation, or shear cannot work with our data, because when we try to perform random rotation, we are basically just changing the latitude and longitude values. Translation can cause in losing some of the cyclones which are at the end of the image, and shearing also can cause losing of some of the cyclones. So we had to think about new methods of how we can do this augmentation, and then we switched to flipping and noise addition. So even with this flipping, in the next slide, I'll show what exactly I mean by flipping. And even with flipping, the results improved marginally. Like we did not see a major improvement. So here you can see that what I mean by flipping. So here we have like the upper one is the original image and the bottom one is the flipped image. So this provides us with more data and more instances of these different classes. So this kind of augmentation to perform, like other augmentations could not work with our case. Yes, so the lessons learned from this overall thing is that the detection works really better when we have this high resolution data. So like I mentioned, we had this data at different resolutions. So it's always better to go for high resolution data. In case you cannot obtain this high resolution data and you only have this low resolution data, then this augmentation techniques can help. We're actually trying to combine this, like adding noise with flipped, and like that can lead to this 4-fold, 8-fold of data and try with those experiments. Then another important point is this aggregation of classes. So it's always better to have this less classes with more samples rather than more classes with less samples. This again depends on the data quantity of data, but it's like this worked for our use case. And this the approach of using classification with cutouts, it can work with more data, as the authors did in the previous approach. They had data from around 35 years, and that's why it worked really good for their case. But since we had only 4 years data, it did not perform really well for our use case. There's also this case of empty cutouts. Like in some cases, the cyclone is observed in the next frame within a day. Like I mentioned, we have 4 frames for a single day. So sometimes the cyclone is observed within frame 3 and 4, but it's not there in frame 1 or 2. But still, the labeling is done for both initial frames as well. So this affects the overall accuracy of detection as well as classification. And that's why we need some form of manual inspection on the data. But it's not feasible, and that's why we just go ahead with whatever data we have and see if it can perform better. Yes, so currently the next steps are, as I mentioned, so in this task, we focused on the detection work, and the tracking is performed as a post-processing step where we check for this coordinates predicted by the regression model and then connect them across these 4 frames for a single day. So the next idea is to add end-to-end tracking with the use of temporal context. So passing this 4 frames on a single day, and then let the network learn to have this, if it can see the cyclone in the first one, but it is there in the next 3 frames, then it should be able to track that as well. As I mentioned before, we have this label noise where there are some empty frames. So we want to reduce that, and that can improve the detection. And the most important thing is to integrate all the notebooks that I have, all the experiments that I've done into one library, which is currently being developed at ECMWF. And I'll be working with Pedro, my mentor, after this, like to integrate this modules into this library. Yes, so the things that we learned, it's like, for me, it was mainly like, it was new for me to work with satellite imaging data. I had to do this resolution specific data management, like different data formats, GRIP data format and all. I had to learn this, like write the scripts to get this data in the right format that we want to pass for these algorithms. We also had to work with advanced techniques in object detection, and we formed new ideas to combine and how we can go for tracking. And the most important thing is this discussions with mentors, which help to like address all these issues that we had, and also providing new ideas like how we can improve this further. And below are the learnings from my mentors. Okay, so these are the results that we have. So green ones, so this is just for the tracking part that we have. The green ones are the original ones, and the blue ones are the predicted labels. I actually have a video to play. So I actually uploaded the video, but the quality doesn't seem to be that good. And that's why I had this previous thing as well. So and yes, that's it from my side. I'll be happy to take any more questions.
Many thanks, Ashwin. Wow, a super project. Thank you very much.